Hello everyone, welcome to another video tutorial of the FEMM software. In this video, I am going to solve a magneto-static problem. This is the structure of the problem. I am going to calculate the magnetic field that is generated by this coil inside this iron yoke. As you can see here, we don't have any air gap in this iron yoke. We have a closed iron yoke, and I am going to calculate the flux density using the finite element software FEMM, and also calculate it by analytic method. As you know, this is a simple problem and we can solve it using magnetic equivalent circuit method. And finally, we will compare the results. So you can see dimensions here in this figure. This is a 3D model of the structure, and for 2D simulation, we should simulate this cross section of this structure. So let me open the FEMM software and create a new problem that is a magnetics problem. And now we should generate the geometry. So you can see dimensions of the structure here. The width of the yoke is 1. The length of the yoke is 10. Also, the depth of the yoke is 1. So the unit is centimeter. So from here, properties problem, I select the length unit equal to centimeters, and everything is okay. Okay. So first of all, I should create points or nodes. So I press the tab key on my keyboard and I press 0 and 0. We created this point. Then I should create this point, this corner point here. I press the tab key. This is 10 and 0. Tab key 10 and 10. This point. And finally tab key 0 and 10. These 4 points. So we can draw this square, this edge, this edge, this edge, and this one. Now I am going to define points for creation of these 4 inside edges. So I press the tab key, 1 and 1, 9 and 1, 9 and 9, and finally 1 and 9. So I can select segment here and draw the closed iron yoke. This one. Also, because we are going to simulate this cross section, we have 2 rectangles here, actually 2 coil arms, this coil arm and this one. From here, you can see relative dimensions. If I show you, the clearance distance between the coil and iron is 0.2. Also, the clearance distance here is 0.2. So I select the point and I press the tab key. I write here 1.2, 1.2, this point. Also, the width of the coil is equal 1. Let me select this one. This is much better. This is the width of the coil. Actually, if you consider this dimension, the width of the coil is 1 minus 0.2. So I can press here and write 2 and 1.2. Again 2. The y coordinate is 9 minus 0.2 or 8.8. Again 1.2, 8.8. So I can draw this coil arm here. And now I am going to draw another arm. So I press the tab key and right here minus 0.2, 1.2, minus 2, excuse me, minus 1, 1.2, minus 0.2, 8.8, minus 1, 8.8, select segment, and yes. So we created the 2 coil arms and closed iron dukes. Let me select this folder and this directory, save the project, this one, I write here closed core. Okay, so as you know, the next step is assigning material labels. So I assign a material label here, a material label here, and a material label here. From materials library, I am going to add the pure iron, and also we need the copper. Let me select this wire gauge, a standard wire gauge, 22, press OK. So I can right click on this label and a space key. Block type is, we can set the material. Block type, material is pure iron. Block type, material is copper. Okay. So, for magnetics problem, we should define a region or an enclosure, right? Because we have flux inside this iron core. Also, we have leakage flux. So we should consider a region to simulate our infinity of this problem. So we have two coil arms and one iron core. As you know, we will have linkage flux and also leakage flux. So we should consider a region and apply a proper boundary condition on this region to confine the solution region, to confine the flux inside this solution region. So the dimensions of this solution region is important, right? Should be large enough to simulate the structure adequately. This is the maximum dimension in our structure, right? I'm going to, because this is 10, and this maximum dimension is 10 times square TL2 or 1.41, that is around 14. I'm going to consider this equal to, for example, 20. And this equal to 20. So here I select the node, I press enter, I write here minus 20, minus 20. This point, right? And because this is a closed core and we don't have air gap, even we can consider a lower number. Let me start with minus 10. So let's delete this point. Again, I press tab key, minus 10, minus 10, 20, minus 10, 20, and 20, minus 10, and 20. These 4 points. And then let's draw segments. Okay, this is the region or enclosure. So we have two air regions. The first one is this one, and the second one is this one. Also from material library, I add air. Okay, right click, space, block type is air. Right click, space, block type is air. Okay. The next step is definitional boundary conditions and then excitations for these two coil arms. From here, properties, boundary, I add a new boundary condition. I write here A equals 0. A is magnetic vector potential. And when we set the value of A equal to 0, the flux lines will be tangent to the outer boundary. So I write here the name. I press OK. OK. Select segment. Right click. Space. This is boundary condition here. Right click space. Boundary condition. Right click space. And right click space. So I applied 4 boundary conditions on these 4 edges. The next step is definitional excitations. If we have n turns for this coil, nt, number of turns, and if we have this current, I, so the total current that is flowing in this coil arm, the current here is inside the paper and here is outside the paper. This is the total current, negative of NTI, that is in this is for this coil arm, and the value of current here is NT times I. Here I am going to consider N times I equal to 100, or 1 ampere times 100 turns. You can suppose that the number of turns is 100. So for definitional excitations from here, circuits, I add a new circuit. I write here coil in, the value of current is minus 100. Add another coil out, the value of current is 100. Okay. So again, I select the material label here, select this label. If I zoom in, select this label, press tab key. In circuit, yes, is a coil in, number of turns is 1, because I considered 100 amperes. And here I press, this is coil out. So everything is okay, and I can generate the mesh and solve the problem. But I am going to change some properties of the material, because I am going to solve this problem analytically. I am going to consider a linear magnetic property for the iron. So from here, properties, material library, pure iron. From here, materials, I select pure iron and modify its property. I don't want to consider a non-linear pH curve. I am going to consider a linear pH curve and set the value of relative permeability equal to 4000 for mu x and 4000 for mu y, and press OK. So this is a linear magnetic problem. If I draw the equivalent circuit of this problem, we have this magnetic equivalent circuit. We have a voltage source here and a resistance. This is the reluctance of the core. The value of this source voltage is N times I. So the value of P, magnetic flux, is equal, phi is equal Ni divided by reluctance of the core. And you know that the reluctance of the core is 1 divided by mu times L divided by A. L is the mean length path of the flux tubes that I will show you. So if I solve this problem, let's see the results. We have flux lines here. Also, I can plot the flux density in Tesla, show density plot. Okay. You can see the value of field here, that is 1.46, right? Here we have a uniform distribution. and here we have non-uniform distribution. As you can see here, the value of amplitude of B is changing. So this is the exact solution using the finite element method. If we want to solve this problem analytically, we should solve this equivalent circuit. So here is my calculations. The widths here, the width of the yoke is 1 and the depth is 1. So the cross section of the core is 1 times 1. Here I have the unit here is meter, right? And also the unit here is, let me check. The units are in centimeter. So here if I want to consider meter, the width here is 1e minus 2, and here I have 1e minus 2. So this is meter square, right? 1e minus 2, 1e minus 2, that is depth. Cross section area is width times depth. Width times depth. And the mean length, what is the value of the mean length of the flux density? I mean this length in the middle of this closed iron core. That is equal 4 times 9 or 36, right? Here, if you see dimension, this is 10 in the middle of this leg and this leg, the distance is 9. So we have 4 times 9, that is 36. So I write here 36 e minus 2. So the mu 0 is permeability of the vacuum, that is 4 times pi times 1e minus 7. This is relative permeability of the iron, and this is the permeability of the iron core. So the reluctance of the core is equal to the mean length divided by permeability of iron core times the cross-sectional area, this equation. And we have this MMF. So the value of flux is MMF divided by reluctance of the core. So when we have flux, we can calculate the B. As you know, the value of phi, is equal B times A. So the value of B is phi divided by A, or cross-sectional area. Here the value of A is 1e minus 4. So the value of B is the flux divided by this value, that is 1.4. So this is analytic calculation, and we didn't consider the effect of leakage flux. But as you can see here, the results are close. If I click here, the value of B is 1.46 Tesla, and the value here is 1.4 Tesla. Right. So, okay, this was the first magnetic problem, linear magnetic problem that we solved in the FEMM software. So I hope you enjoyed this video. Let's continue in the next videos. Thanks for watching.